Mhm. Okay, so good afternoon, everyone. This is our last stretch for this class. We have 3 hours today. I don't know why on the calendar I had 3 more hours between 4 and 7 p.m. for us, which is impossible because it will be 10 p.m. for you. So that was a leftover. But this afternoon will be the last 3 hours. And so, as I told you, my former PhD student Camilo Riaño is now Dr. Riaño and working as a postdoc on an Air Force project and also leading the development of the D3 CubeSat. Has kindly agreed to show you some of his work on combining the torques that we have seen, the gravity gradient one and aerodynamics, some of those that we have seen, using the D3 CubeSat with the deployable surfaces to control orientation of the satellite on 3 axes. So before I give him the floor, Camilo is originally from Colombia, where he got 2 master's degrees, and joined the University of Florida a little over 3 years ago, where he got his PhD in mechanical engineering. And so yeah, I think I gave you all the information about him. The paper that goes with this presentation is in the folder with today's date and also the slides. And with that, Camilo, very informally, just explain your work. And if you guys have questions, I think they can probably interrupt you and ask. But I guess the floor is yours. Feel free to share. Thank you.
Thank you. Let me know if you can see my screen.
Yep.
Okay, so yes, thank you for the presentation.
Can you make the presentation mode maybe? Yeah.
All right. So yeah, as you said, thank you for the introduction, and it's nice to be talking to you today. I have been, as Dr. Bevilacqua said, I am part of the Advanced Autonomous Multiple Spacecraft Laboratory, ADAMUS, here at the University of Florida, where I have worked mostly on both orbital and attitude control using environmental forces and torques. And this talk today is mostly about the environmental torques for attitude control using the drag maneuvering device, which was designed here at the ADAMUS lab. Okay, so the outline of the presentation is as we have here. First of all, I will present some brief motivation for the problem. We will go over some concepts of aerodynamic torque and gravity gradient torque. Then I will present the drag maneuvering device, which, as I said, it was developed here at the ADAMUS lab. And finally, I will present 2 different approaches for attitude stabilization and control using the drag maneuvering device to combine both aerodynamic torque and gravity gradient torque. Finally, some conclusion for this presentation. So let's start with the motivation. So the increasing popularity of the small satellites serves as the main motivation for this type of techniques. It's mainly because they have been used like in a standardized way using the CubeSat standard, and it has reduced the cost. And we also nowadays have access to high performance hardware with a reduced size that allows us to accommodate enough power for processing controllers or anything like that on small platforms. Some limitations for these type of platforms are, of course, the reduced volume to accommodate the propellant, which is, of course, a problem if we want or if we attempt to control the attitude of the spacecraft with, for example, thrusters. And some of them, especially CubeSats, are launched as secondary payloads for larger missions, meaning that they can also have some additional constraints to have a propellant due to safety constraints. Also, the commercial attitude determination and control systems are among the most expensive components for small satellites. They are usually in the orders of tens of thousands of dollars. and that represents also a problem for small platforms, especially in academia where the budgets are limited. This picture here, it's showing the main perturbations for the attitude of a satellite, standard satellite. These perturbations are in different regimes. So the regime we are interested in is the low Earth orbit, which is usually below 700 kilometers or 1,000 kilometers. The two effects that are the most important are the gravity gradient torque and the aerodynamic torques, which are the green line and the blue lines respectively. Usually the aerodynamic torque and gravity gradient torque have been considered disturbances in the low Earth orbit. So actually this picture is called disturbances for the attitude of a spacecraft. So the controllers that have been developed throughout the years have been designed to overcome the influence of those perturbations on the spacecraft attitude instead of using them to actually control the spacecraft. So this new approach is motivated by the increase of the small satellites' popularity, and exploiting the aerodynamic torque and gravity gradient torque has become an option for controlling the attitude without using any propellant, and that is mainly the motivation for this. In order to achieve that goal, new spacecraft designs have been proposed also throughout the years to increase the magnitude of gravity gradient torque and aerodynamic torque to have like a bigger influence on the attitude of the spacecraft. This is the way usually the Euler's law is seen for control purposes. So we have the time derivative of the angular momentum as seen by the inertia frame, and here we have the external torques, which are usually the control torques. And then we have this disturbance vector that contains the attitude, the aerodynamic torque and the gravity gradient torque and some others. But now we are just going to consider that this external torque is zero, and we will just use the disturbances for controlling the spacecraft. So first of all, I will need to introduce the aerodynamic torque. So as you probably know, the aerodynamic is the largest non-gravitational force acting on a satellite in the low Earth orbit. It also depends on several parameters, and some of them are very difficult to model, such as, for example, the atmospheric density, which we call ρ, or the drag coefficient, which represents the interaction of the surfaces of a spacecraft with the atmosphere, which we call drag coefficient, or CD. So the drag and lift coefficient, the drag and lift forces are expressed by these equations. So the drag force is the one that has the biggest or the largest influence on the among the two different aerodynamic forces, and it is mainly because this drag coefficient has some orders of magnitude is larger than the lift coefficient. It also depends, as I said, on the atmospheric density. Here, S is the surface area. So in this case, the drag and the lift forces are expressed for the jth surface of the spacecraft. So we can discretize the spacecraft with different surfaces and compute these. So we can change the surface area by, for example, deploying panels that interact with the atmosphere in such a way that we can modify the magnitude of the forces. Then we can, of course, compute the aerodynamic torques due to drag and lift by using just this cross product between the vector that goes from the center of mass to the center of pressure, and just apply that as many times as we have surfaces on the spacecraft. The velocity vector relative to the atmosphere. So you see here in the drag and lift forces expression, we have this vector VR, which represents the relative velocity of the spacecraft with respect to the atmosphere. And we have to take into account how the atmosphere rotates or moves with respect to the spacecraft. So this is the most common expression that we can use for that relative velocity. and it assumes that the atmosphere is co-rotating with the Earth. So this angular velocity is just the Earth's angular velocity, and RC is the position of the vector. So here we have the velocity vector of the spacecraft, and here we have the influence of the rotation of the Earth. This is an example of a design of spacecraft that tries to use the aerodynamic forces to modulate the or to regulate the attitude of the spacecraft. This is from this paper by Sun. It has a main hub, which is just the body of the spacecraft, and 6 drag surfaces, which has each of them has 2 degrees of freedom, so they can be extended, retracted, and they can also rotate about the longitudinal axis. So by modifying both the angles and the size of those big surfaces, they can generate torques with respect to the center of mass, so that they can modify their attitude. Regarding the atmospheric density models, there are several with different levels of accuracy. The simplest one is the exponential model, which is just taking into account the fact that the density decreases as the altitude increases. So it is embedded in this exponential function where the rho naught and h naught are tunable parameters, which are available in lookup tables, which were calibrated based on observations. More detailed models can also account for chemical constituents, temperature, radiation from the sun, geomagnetic storms, and so on. There are some purely theoretical models, such as, for example, the Harris-Priester, and there are also some which we call semi-empirical models that also include measurements taken by satellites that actually flew on the low Earth orbit, and those were used to calibrate some parameters that are used in the model that actually estimates the atmospheric density. So even the most detailed models, such as the NRLMCs or the JACIA, require forecasting some indices for the real-time onboard operations. So you can imagine that you have some spacecraft which compute some control law on board. It needs to compute the estimate of the atmospheric density at any time, so that it can compute the aerodynamic torque that it's applying. So in that case, forecasting of those indices would be required, and forecasting means that we are introducing some estimation error, which is also a problem for these kind of techniques. On the gravity gradient torque side, so the gravity gradient torque is produced by the gradient of gravitational forces along the spacecraft body. This is the general expression for the gravity gradient torque, where G is the universal gravitational constant, M is the mass of the Earth, RC, as I just said, is the position of the spacecraft, and J is the inertia matrix. So as you can see in the expression, the gravity gradient torque mostly depends on the orbit states, but by modifying J, we could actually change the gravity gradient torque, and that is actually what people do when trying to use this effect for controlling or stabilizing the attitude of the spacecraft. So in general, the gravity gradient torque is smaller than the aerodynamic torque in the low Earth orbit, but it has some nice stability properties that can be actually exploited to be combined to aerodynamic torque and actually achieve 3-axis attitude stabilization. In this case, this is just an example of gravity gradient torque application. So this is the SpriteSat microsatellites from the Tohoku University, where they have the main body of the spacecraft. Once it was deployed, it deploys a long boom with a tip mass that produces a clear minimum moment of inertia about the vertical axis, and it uses some gravity gradient stability conditions to ensure that the spacecraft remains in the vicinity of nadir pointing. So to study the gravity gradient stability, we will need to make some assumptions. which will help us coming up with the model that I will show you later in the presentation. So first of all, the goal on space applications regarding the attitude, it's to have some orientation with respect to the orbital frame usually. And the assumption that we will make here is that the spacecraft is in a circular low Earth orbit, which means that the angular velocity is constant. That also there are just small departures from the equilibrium point, which is alignment between the body frame and the orbital frame, so just like small angles with respect to that orbital frame. And also that the inertia matrix is constant when expressed in the body frame, which is also a common assumption for expressing the Euler's law. These are the three main reference frames and the attached coordinate system. So we have the inertia frame with center with origin at the Earth's center of mass, denoted by the bases x, y, and z. For the orbital coordinate system, we have the blue one with origin at the spacecraft center of mass and the bases O1, O2, and O3. And the body coordinate system, which is the one that actually rotates with the spacecraft, with origin at the spacecraft center of mass and denoted by the bases B1, B2, and B3. So when we compute the equations of motion, we need to have an expression for the angular momentum, which is commonly expressed as the product between the inertia matrix and the angular velocity with respect to the inertia frame. And once we take the time derivative for the Euler's law, under the assumption that the inertia matrix is constant, then we can obtain this expression by just applying the transport theorem. This is the equation of motion we get, where the only torque that is influencing those dynamics is the gravity gradient torque, because we just want to observe what the influence of this torque on the attitude dynamic is. And then for visualization purposes, we would represent the orientation of the spacecraft using a 3-to-1 Euler angle sequence with respect to the orbital frame, with phi, theta, and psi being a rho, pitch, and yaw. So here we can express the angular velocity of the spacecraft with respect to the inertial frame as just the addition of these two terms, where this first one is the angular velocity of the body with respect to the orbit, and this one is the angular velocity of the orbit with respect to the inertial frame. So in the second term, we know that it is just driven by the angular velocity of the orbit about the axis, the orbit axis O2. And we can apply the 3-to-1 Euler angle kinematics to compute the angular velocity of the body with respect to the orbital frame as a function of the angular rates. Then we can take the time derivatives for these expressions and also apply the angular approximation, and this is what we will get. So we get the angular velocity under the small angle approximation here as a function of the rho, pitch, and yaw rates, and also the orbit angular velocity. And then we can take the time derivative and obtain omega dot. We can do the same for the gravity gradient torque. We can just take the direction cosine matrix and apply that for the position vector and express everything on the body reference frame. And this is the expression we get after applying the small angle approximation. The linearized equation of motion then is this set of three equations that we have here, where the first one is for the roll dynamics, then the pitch dynamics, and then the yaw dynamics. So as you can see here, the pitch dynamics are decoupled from the other two. We don't have influence of roll or yaw in this second equation. So we can study the stability of these single equations separately from the other two. So essentially, we just need to make this coefficient to be greater than 0, and then the system will be stable. And that is exactly what this condition is saying. And then we can compute these modified variables, which are K1 and K3, and they are just these ratios of inertia. And this is the way they are usually shown in a plane of K1 and K3. And then we will start coloring some areas that will show where the spacecraft is stable and when it is unstable. So the shaded region or the green region is the one that is unstable, and the white region is the one where the spacecraft is stable. So if this is stable, so if we are in the white region, the system, the pitch dynamics will have two imaginary eigenvalues, which means that the spacecraft will oscillate around zero, and there will be no damping. Essentially, we don't have like a theta dot here to provide the damping, so it will be oscillate in the vicinity of alignment on the pitch axis with respect to the orbital frame. And then the roll and yaw dynamics are coupled with each other. So here you can see the influence of the yaw on the roll dynamics and the influence of the roll on the yaw dynamics. And we can express these as a state space representation and obtain the characteristic equation, which is what we have here. This characteristic equation is a fourth order equation, but as you can see, it has only s to the fourth, s to the second, and then s to the zero. So we can solve for s to the second and then take the square root and obtain these two different conditions, which say that this, if we satisfy these equations, then the spacecraft will be stable. So the white regions then are the only regions where the spacecraft will be stable for both the roll-yaw couple dynamics and also the pitch dynamics. So if we look into these white regions, the big one here, the whole triangle, would mean that J2 is greater than J1 and greater than J3, meaning that the spacecraft will travel in this configuration where the skinnier axis is the one that is aligned with the vertical axis of the orbit. And then this second one is this whole triangle means that J1 is greater than J2 and greater than J3 and greater than J2. So if we take into account all the triangle, that would be the condition. But since we have only just a portion here, then just a subset of those of this condition will be the one that provides stability. Given that this is very difficult to warranty, essentially that we are inside that specific subset, then usually this is what people use for stabilizing the spacecraft by gravity gradient torque, and that's what we just saw on the SpriteSat example previously, where the boom was along the vertical axis, so that it was skinnier along that axis, and the minimum moment of inertia was about that axis. And then this is the drag maneuvering device, or we previously called it the D3 or drag deorbit device. We just decided to change the name because we are now using it to maneuver not only the orbit of the spacecraft, to change the orbit of the spacecraft, but also to modify the orientation. We are just actively maneuvering the spacecraft. So the drag maneuvering device is it can be attached to standard CubeSats, and it has 4 drag surfaces in a dart configuration, which provides stability about yaw and pitch by just having this inclination and putting the center of pressure behind the center of mass. So those surfaces are offset 90 degrees with respect to each other, and they also have a 20 degrees inclination. They are, each one is up to 3.7 meters long, and they could provide another cross-sectional area of 0.5 meters squared. The weight of all the booms together is about 0.5 kilograms. So when it is attached to CubeSat, for example, a 2U CubeSat, which is around 3 kilograms, it could significantly affect also the inertia matrix, and that's something that we wanted also to exploit for modifying the or through controlling the attitude of the spacecraft. So how can we change the aerodynamic torque by using the drag maneuvering device? So we will keep the same assumption of the small angles for now. And let's consider the drag force. So this product between WB and LJ, where J is just like the J surface. So here we have 4 surfaces. This is the area of the surface, where WB is the surface's width, which is constant, but we can change the length as to have the specific value that we wanted. So by changing that, we can modify the amplitude of the drag force and use that for modifying the aerodynamic torque. The vector Rj then is just the addition of these 2 vectors, where Rc is the vector that goes from the center of mass to the geometric center of the rear face of the spacecraft, and then the vector Rj that goes from that point to the actual center of pressure. So as I just said, the DMT surfaces are in a dark configuration, which allows aerodynamic passive stabilization about the second and the third axis. So you can imagine that you can have an unbalanced here. So you can have, if you have them equally deployed, the torques applied by the surface L1 and the surface L2, they will cancel each other when those when the body frame and the orbital frame are aligned. And the same will happen with L2 and L4, modifying the torque about the B3 axis. And then how can we change the gravity gradient torque by modifying the surfaces of the DMD? So first of all, we will need to model how the inertia matrix changes with respect to the surface's length. So we discretized the D3 in several subsystems or sub-bodies. The CubeSat body will be a rectangular box. The roll portion of the boom is a thick-walled cylinder, which we know the moments of inertia for those shapes. And the outer diameter, which is R2, will be a function of the length of the boom. So we can have expressions for the moments of inertia as a function of L. And the same for the deployed portion. It will be a flat plate, and one of these dimensions would be the length, so that the moments of inertia are also a function of L. So we can first find all the inertia matrix for each specific shape individually, and then we can apply just rotation of the inertia matrix to have them align with the principal axis of inertia, and then we can apply parallel axis theorem to bring those to the center of mass, and then add them all together so that we can have the entire inertia matrix as a function of the length. So we did some small simulations for proving this approach. The goal is to combine aerodynamic torque and gravity gradient torque for attitude stabilization. So we are trying to achieve pitch and yaw stabilization by using the aerodynamic torque, essentially just keeping the vertical surfaces, which are L1 and L3, at the same level, and the horizontal surfaces are the same level, which are L2 and L4. So we have L1 and L3 equal to 3 meters, and L2 and L4 equal to 1.5 meters. So as you can see here, the vertical ones are much longer than the horizontal ones, which provides a clear minimum axis moment of inertia about the vertical axis, which is exactly what we want to satisfy this gravity gradient stability condition. So here in this simulation, I have the examples with applying by satisfying the gravity gradient stability condition and well, not satisfying it and then satisfying it. So if we don't satisfy that, here we can see the pitch and the yaw stabilization by aerodynamic torque, but the spacecraft will still be spinning about the first body axis, which means that the roll angle is diverging. And then if we satisfy this condition, which is just putting all these surfaces at the same at these levels, then the gravity gradient torque will help us keeping the roll angle also bounded, which is the goal for the attitude stabilization. So up to this point, we have seen that the aerodynamic torque and the gravity gradient torque can be combined for achieving attitude stabilization. But we have, as you have seen, we have made several assumptions, and they might be too restricted for a real operation scenario. So there are some problems. The first one is that we are assuming that we completely know and we can precisely achieve the length of all the surfaces to be at the levels of deployments that we want. But it is not usually the case because there are construction tolerances, and it may produce some residual aerodynamic torque that could drive this CubeSat to be beyond the limits for the small angle approximation, and then all the stability that we have studied will not be guaranteed using this approach that we just presented. Then we can also have a mission that requires not only stabilizing, meaning that keeping all the angles bounded as we have seen, but actually regulating them and bring them as close to zero as possible, or just having the spacecraft with a specific configuration of orientation different from alignment with respect to the orbital frame. So in those cases, this approach of attitude stabilization by just using the techniques that we have shown will be insufficient. And we have also assumed that we know perfectly the atmospheric density and other parameters, which might not be useful if we want to achieve more complicated control objectives. So there are some considerations that we can make to address this problem. The first one is that we can avoid using the Euler angles because there are singularities that could show up when controlling for large angles, which could be the case in a real operation scenario. We should use definitely the full coupled nonlinear dynamics without linearizing it, so that we can take into account all the coupling between the three angles, or the three angles, if you want to look at that. We can also dynamically change the length of the DMD, not just keeping them fixed, but actually change them dynamically following some control law to help damping those residual oscillations and achieving better pointing results. And we can also incorporate adaptation capability to compensate for uncertainties, for example, in the atmospheric density and some other parameters. So this is how the Euler's law would look like in the case that I just described, following the considerations. The first one is that we have an additional term, which is the J dot, and this is just because if we change actively the lengths of the drag surfaces, then the inertia matrix will also change, even if we express that in the body reference frame. So if we take the time derivative of the angular momentum, then this additional term will appear. And then we have same two terms here for the rest of the dynamics, and then the aerodynamic torque and gravity gradient torque. On the drag and lift forces, we will have some uncertain quantities, which are usually the most important ones, the atmospheric density and the drag and lift coefficients. So we don't know exactly their values, and we need to compensate for that uncertainty. Then we can express the orientation of the spacecraft with the Quaternion. So this Quaternion is a representation of the orientation of the spacecraft with respect to the inertial frame. It has a scalar and the vector part. It has to have a unit norm, And this is the Quaternion kinematics, which is just the equation that relates the quaternion rates with the angular velocity of the spacecraft, and it is also a function of the quaternion itself. So if we look in more detail into the dynamics, all the circle terms are the terms that we can actually modify by changing the length. So we can change the inertia matrix, its time derivative, and we can also change both the aerodynamic and the gravity gradient torques. So it looks like we can affect a lot of terms, meaning that we have reasonable control authority over the system, but the control inputs are all over the place, and we have to come up with a controller that actually takes that into account and help us taking the most from the use of the DMD device. So this is just the error quaternion, and it is useful in cases where we want to not only achieve alignment with respect to the orbital frame, but also that we want, for example, to track some reference, or we want to have like a specific orientation with respect to the orbital frame. So the error quaternion, it's just this expression, which is function of the Q, which is the actual quaternion, and the QD, which is just the desired quaternion, and that it's just some input, reference input that we can provide to the system. It also has to comply this unit norm condition, and the error quaternion kinematics look very similar to what we previously saw for the quaternion. The difference is that it is a function of the error quaternion components, and also this omega tilde, which is the relative angular velocity defined by this expression, where we have the actual omega of the body, and this omega d, which is the desired angular velocity, which is also provided as a reference to the system. And R tilde is just a rotation matrix that brings this vector omega d to the same reference frame as omega. Then we can start defining some useful variables. So this is just what we call an error signal. So it has information about the error on the quaternion, but also the error on the angular velocity, because the EV dot, as we have seen in the error quaternion kinematics, is a function of omega. And then if we take the time derivative of this vector r, this is the expression that we will get, where omega, where y theta, it's this complicated expression, but this is just an expansion of the attitude dynamics. So if you take the time derivative of EV, then you will have some expression of omega dot. And from the dynamics, we have omega dot here. So essentially, we can just solve for omega dot on this Euler's law. And then we can plug in omega dot into this time derivative, and this is part of the expression that we will get. We are calling it y theta, and it is just two terms because it's a linear parameterization with respect to the uncertain parameters, which in this case are all in the vector theta. So theta contains, for example, drag coefficient, which we don't know, atmospheric density, and we could also include the lift if we wanted to. The y is the measurable regression matrix, so it's just the matrix that makes this product equal to this equation, including the dynamics. And it contains only measurable quantities and things that we can compute, such as, for example, the inertia matrix, or the error quaternion, or the angular velocities, which are assumed to be measurable. Then we can start developing our actual controller to modify the attitude of the spacecraft. So this is what we call the auxiliary controller. It's just a vector that contains all the parameters that we can manipulate. So we can manipulate essentially the four lengths of the booms, which are all embedded in the vector, in the matrix Y, as you can see here. So if theta, it's just this expression, then all the j's, which are function of length, and also the remaining of the aerodynamic torque will be a function of the length, which is exactly what we have here. So this is the vector that we can manipulate, the matrix that we can manipulate, and this vector theta hat, it's just an estimate of theta because we don't know theta precisely. And then we can design a control law by just using standard Lyapunov theory, and I will show the proof, an overview of the proof later on the presentation. But the main idea is that here we have a feedback term of R, which is the modified state that contains E dot and also E, the error quaternion. It also has the time derivative of the error, the vector portion of the error quaternion and the error quaternion itself. And K, alpha, and beta are just constant control gains that we can tune depending on the control authority that we have on the system. So the goal is, this is what we desire. So this is the torque that we need to apply to the system so that we can make it stable. And then we have to reproduce that torque by modifying this product between Y and theta hat. So we have to do two different things. We have to compute some estimate of theta by designing an update law. And that's I will show that later in this slide. And then we can modify the length to make this product to be as close as possible to UD. So we can define the estimation error, which is just the difference between the actual uncertain parameters, which we don't know, and our estimate of the uncertain parameters, and we call that theta tilde. And then we can plug in the control law, which is the expression we have here, and this is the expression that we will get. So here we have the what we call the closed loop error system, which contains the effect of the controller and also the dynamics of the system. And then this last term is just to include the possibility of having some small mismatch between the U bar and UD bar, just because, for example, we could have some construction limitation, or we could have saturation on the actuators. So to account for those differences, we have defined this vector chi. And the way we design this theta hat, it's by designing its rate of change, which is theta hat dot. And it's used, we can integrate this expression to obtain theta hat and plug this in at any point in time so that we can compute U bar in real time. So this is the expression we have here. Gamma is just the adaptation gain, which is a constant that we can manipulate to determine how fast we want to change our estimation. The Y is the regression matrix, which, as I said, it's measurable, so we can have this quantity computed at any point in time. And the R vector is just a vector of the states that we assume that we can measure. So if we design that control law, which we called UD bar, and also the adaptation law, which is theta hat dot, then we can show by using a Lyapunov stability analysis that the attitude error converges to the vicinity of 0, meaning that we can achieve bounded tracking with respect to the reference that we apply to the system. So this is an overview of the proof. We just propose a candidate Lyapunov function, which we call V. This is a scalar function that contains information about all the states of the system. So we have R and EV. So here we have angular velocities. Here we have the orientation of the system. And it also contains information about the estimation error, which is theta tilde. And then we can express everything in terms of this composite error vector, which contains information about R and EV. So as you can see here, all these terms are quadratic terms, meaning that this function V is positive definite. So if we have a positive definite scalar function and we take the time derivative of that function, and it turns out that the time derivative is negative definite or satisfies some conditions, then we can show that all these states that are inside V also converge to 0. So if we take the time derivative and substitute the closed loop open loop error system, which is essentially R dot, this is the expression we get. So here we have a quadratic term with this K matrix, which is a control gain that we can define to be a positive definite. So this will be negative definite in terms of R, and this other term has a similar form, which is a negative definite term in terms of the vector portion of the error quaternion. And then we have this residual term, which is just upper bounded by a constant, and we have to take that into account on the final result. Then we can invoke the comparison lemma to get the solution for this differential equation. So here we have the behavior of the Lyapunov function over time. It's just an exponential expression of some negative coefficient of t. So this converges to 0 and starts from the initial conditions. And here we have just a residual term, which comes from this residual chi. Then we can start changing from V back to Y and then back to R and EV. So that's what we have said here. This Y being part of L infinity means that this is bounded, which is something that we need to prove in order to show that the system is stable. So then we can say that R and EV are bounded, and then all the other signals on the dynamics of the system are also bounded by just looking at the dynamics. So then the result in terms of Y is saying that the norm of Y is smaller than this expression. So it's upper bounded by this expression, which is a decreasing function. If B1, B2, and B3 are positive constants, which they are. So if they all are constants and we know the values of the constants, we can say that the states inside Y, which are R and EV, they also converge to 0. But since we have this ultimate bound, which we cannot, essentially we will be as close to 0 as B3, as the value of B3. So this is the ultimate bound, and that's why the attitude error system converges not exactly to 0, but to some vicinity of 0, depending on how good our estimate of chi, or our value of chi is. We conducted some simulations just to show all that theory. So the simulation takes into account the physical properties of a 2U CubeSat with a DMD device, and it also takes into account all the spacecraft nonlinear attitude dynamics. So the initial orbit for the system is 400 kilometers altitude orbit, similar to that of the International Space Station. The physical characteristics of the spacecraft are as shown in this table, and we selected the control gains as we have here. So we have alpha, beta, and K as we have here. So they are positive, definite matrices, and they are constant, and this is the adaptation gain, which is helpful for estimating the uncertain parameters. The initial conditions for the regulation objective. So what we call regulation in this case is just bringing the attitude of the spacecraft to a certain orientation fixed with respect to the orbital frame. So as you can see here, our roll, pitch, and yaw, and this is just showing this for visualization purposes. All the computations in the controller are made using quaternions, but then we are plotting also the Euler angle equivalent and the initial conditions just to have them like with more meaningful values for us. So here we have larger values, so they don't satisfy the small angle approximation, and we are still able to drive the system to the desired state. Angular velocities, as we have here, and the desired values are 45 degrees on the roll axis and zeros on the pitch in yaw. And here we can see the behavior of the quaternion. So this is what the controller was actually trying to do. We have some reference of the quaternion, which are the 4 dashed lines being QD. And then we are driving all the solid lines, which are representing the Q to be on top of the QD. And on the Euler angles equivalence, so we have the reference for the roll angle at 45 degrees and the other at 0, and you can see that they are converging to the vicinity of those values. They have some small oscillations about that if you zoom in, but the overall behavior is very good as compared with the previous approach. The length of the booms, you can see how they behave here. So they are independently changing over time, and by doing those changes of deployment levels, they are modifying the torques so that this result is achieved. This second simulation is for a different objective. So in this case, it was a tracking objective with respect to the orbital frame. So we have a time varying reference for the roll, and here was the result. So same thing, initial large angles and time varying reference for roll. The behavior of the quaternion, it's similar. It just takes more time because the maneuver is more demanding. But the behavior on the Euler angles equivalent can be easily observed here. So it takes about 5 hours to have all the 3 angles on top of the references. Here we can see the behavior of the boom length. So they require a lot more control effort, but it is still possible to drive the system to the actual references. And finally, some conclusions. First of all, we have shown that it is possible to combine the environmental torques, such as aerodynamic and gravity gradient, for the purpose of attitude stabilization, and then by using similar techniques as the one we have shown here, we can actually control the spacecraft attitude in the low Earth orbit. If we incorporate the capability of active modulation of the surface's length, we can improve the attitude control performance, and that opens a lot of opportunities for coming up with different designs and configurations of the surfaces, which can be investigated in the future for improved control authority, instead of just using those 4 fixed booms. So it's open for future investigation, and we are interested in that for the near future. I think with that, I will end this presentation. So thank you very much for your attention, and I will take any question you may have.
Thanks, Camilo. So the last maneuvers, remind me, we have you track LVLH, but on one axis you're oscillating. That's the desired.
Yes.
Yeah, I'm just asking because one of the class assignments is to use momentum exchange devices to just track LVLH without any additional motion, but basically they have to stay with the body axis aligned with LVLH. So.
Yes, so it would be similar to this regulation maneuver. The only difference is that this reference would be on 0, and that means that you are completely aligned with LVLH.
Does the audience have any questions for Camilo?
Yes, may I ask a question?
Yes.
First of all, thank you so much for the very interesting presentation. what I would like to ask, if I have understood well, at this stage we are still considering the spacecraft as perfectly rigid, right?
Yes, yes, that's
Okay.
true.
And yeah, sorry.
Yeah, so in reality, as you are probably saying, it's or imagining, it's that those long booms will have also flexible dynamics. So we should probably include those into the dynamics and start developing controllers around that. And that's actually something we are working on right now. But yeah, definitely those long booms would mean flexible dynamics.
Okay, no, it was exactly this. But I was looking at this plot in which I think you spent 3 or 4 hours to reach, let's say, a stable oscillation. And I don't know, in this time frame, can you consider that the angular rate is still small and does not affect the rigid hypothesis, or not, in your opinion?
Yes, we actually wrote a paper about that, and one of the comments from the reviewers was on that end. So what we did was just we computed the flexible modes of the spacecraft by using just CAD software, and then we just plotted the applied torques to the system and computed the Fourier transform. And then we just compared the frequencies, the range of frequencies of both of them, and compared against the natural frequencies. And we are still below that. And that is essentially because, as you are saying, these maneuvers using using these environmental torques require a lot of time to be done. And they are just intended to compensate for small deviations and small angular velocities. And in that case that we shown in that paper, we didn't hit the first mode of vibration. We were well below that. But in some cases, if you are, for example, if you are coming up with different configurations and attempting to do faster maneuvers, then you will need to take into account for sure the flexible dynamics.
Okay, perfect. Thank you so much. It was very, very interesting.
Yeah, so the paper that Camilo is mentioning is in the folder today's date, and towards the end you will see there's the representation of the first 5 modes, and you can find in the paper, yeah, the comments, and then just below that plot there is the frequency content of the torque supplied. And so yeah, you can read towards the end this analysis, which is basically saying we're moving slow enough, and we're hopefully not exciting any of those. So yeah, but that's a great question.
Thank you.
Yep. Anything else?
Yes, just a curiosity. In the plot which show the variation of the length of booms, there is a time interval in which the command goes from the minimum and maximum values. For example, the L4 command. And it is feasible with to change the length of the boom so fast in space.
Yeah, so that's actually a good question, and it is also a common question once we submit these type of papers. What we usually do is that in implementation, and it is actually included here, we include after computing the length, we apply a low-pass filter, which helps us reducing the rate of change of those lengths. And given the time frame here, it looks like they are very fast, but you have to take into account that it takes a lot of some hours and some minutes to do that. And in this case, it was we computed the largest rate of change and it was still below the what we have feasible for the D3. It is still demanding in terms of energy, but it is feasible mechanically.
Okay, thank you.
All right. Well, if you come up with more questions for Camilo, just let me know and I can pass them along. So thank you, Camilo, for your time. Really appreciate it.
No, thank you for the invitation.
Yeah, we can let you go. And if the class is fine, I would actually like to continue. If that's okay with you, and we'll take a break in, some time, because we have a 3-hour slot today, and so we'll definitely take a break, but maybe not now. That's okay.
Okay.
All right, Camilo, thank you.
Okay, thank you very much. Have a good day, everyone.
Thank you very much.
Thank you.
Hasta luego.
Thank you.
Thank you. Bye-bye.
Okay, so this is what I was planning to do. A couple of announcements. I checked with Dr. Grassi and Dr. Capocciello, and we agreed that you can take until Friday of next week, the 9th, to turn on your simulating files. And really, I don't envision, being picky with grading. I just need the homework 1 and 2 to run when you send me a package that I can run it without errors and that it plots the results correctly, and I can see that it's doing what it's supposed to do. And of course, this is the last day that we meet formally, but we can keep emailing each other and also meet on Zoom, for example, or even Teams. Why not? As needed. Okay. Let's see. The other thing is, thanks for the 7 of you who have responded to the survey here. Again, it's completely anonymous. I can show you what I see. Yeah, this. So yeah, this is what I see. For different questions. I don't know who responded what, and even if I do go into the specific questions, yeah, I can't see any names, of course. So anyways, when I create let's see, the Excel with different questions and the actual values, and of course it's going to open on the other screen right here. Well, you've been very kind, first of all. I hope you were being honest as well. This is very important for me to this is the first time that I do a class for this program, that I teach a class where the students are abroad, and online is not the first time, but this kind of format is weird for everybody, I think. And so everything is pretty high. The 2 areas where maybe I should improve a little bit are, the expression of expectations. I completely agree. I've been extremely vague in terms of the homeworks. I told you that you have to give me 2 simulating files, and that's the end of the story. And that's because I also, for PhD students taking classes during their PhD, I do not even believe that grading is required. At this point in your academic career, you're learning, you want to learn, you have your thesis to work on. So I was a little too vague, and that can be definitely easily changed in terms of how many points is each one and how do you break it down into points. But what I can tell you now is that you shouldn't worry about it. But yes, that can be absolutely more specific. And the other one is facilitation of learning. So I mean, it's still pretty high, but it's these are the 2 lowest. And so if you have comments, and not now, I mean in general, on how we could improve this class, that wasn't a good screen to see, right? Oops. Please do let me know, okay? Take your time, think about it, send me an email. It would not be held against you in any way. But hopefully the next time around will be in person, so some of these things may actually resolve themselves that way. Okay, so questions, comments, concerns? So today...
Yes, Professor, sorry,
yeah,
I can. As probably you know, I use a different function that comes from the aerospace block set. And I don't know if I have to change all the functions, all the blocks, because when I will send you the final file.
No. Well, no, we do have a license. It's just that it's not directly on my computer. And actually, when I run MATLAB, I have to VPN into my university server. And it's just that I believe we have a certain number of licenses and in the lab. And so if my students are using them, or even they just have something open with that block, even though they don't run it, it counts as a license in use. And so that's really why it usually doesn't work, because there's always someone doing something.
Okay.
But I think I should be able to run it.
Okay, perfect.
It may be not immediate, but yeah. So thank you.
Thank you. Thank you.
And then, so for today, we have a couple more hours left or so. We can press on and look at those slides called Lecture 8. But I think let's see how the Simulink work goes first, because we were leaving yesterday and one of you was working on the variable speed quantum moment gyro Simulink model. We removed that algebraic loop, but still it wasn't integrating. So maybe we can pick up from there. And then another colleague sent me a homework one inclusive of the gravity gradient, which is still not working. So maybe we can dedicate time to those. And the theory in Lecture 8, which is really beyond the scope of this class anyways, which is controlling a 1 degree of freedom a spacecraft with a flexible link and a mass at the tip of that link. It's applying basically the theory that we have seen yesterday. And the novelty there is in designing what is called an input shaping controller, which is exactly what you've seen in the videos. So I think this is something that you can, if you're interested, digest by yourself if we don't get to discuss it today. But I would like to leave you, possibly in relatively good shape with the assignments. So shall we continue on the, if you agree with that? Otherwise, we can go to those slides. But I was thinking to continue on the Simulink model.
Okay,
yeah. So do we have...
Yes.
Do we want to do that maybe? Were you able to fix anything or?
Yes. Okay.
Yes.
Yes, we kind of understood what is the problem with the divergence. And now, okay, so it comes from the derivative, from the numerical derivative. So, okay, here it is. So for the moment, we just commented it in the function that computes the MED torque. So this is our temporary solution. So without this term here, with the gamma double dot that comes out of the, of the numerical derivative, it runs. But just one thing that we were doing wrong was the definition of the error quaternion, because we forgot to invert the body quaternion. So we realized that, and here it is, the function.
You mean the yeah, this one.
Yes.
Let me go back to mine, since we have it here, because I was also not entirely sure it was identical, but then I just got distracted. And go ahead, keep talking. I want to see if mine is.
Okay, yes, because the desired quaternion is the one that goes from the ECI to the commanded attitude, while the body quaternion still goes from the ECI to the body frame. So we need to invert it, and obviously this is just inverting the space component.
The vector one, yeah.
Okay, so
let me look at mine before you go away from that one. I just want to verify. Yes. I had the feeling that at some point I had the feeling that they were different, but we changed topic. Oh, my MATLAB is so slow. It's opening eventually. So you are changing sign to the first three, and
yes, this was the only correction with respect to what we saw yesterday. This one, and then by now we are not using gamma double dot. We are neglecting it.
Okay. Yeah, I think it's the same. It's just that I have it expressed in a different way, so I must have done something. So mine is transpose of that. So it takes 1, 2, and 3. Okay. All right.
Okay.
Keep going.
Okay, so like this it runs, and these are the plots that I obtain, I think. So these are the plots for the quaternions. I had it run for 1.1 times the period, because I saw that something that they were not perfectly aligned when we reached the period. So maybe it's
Maria Grazia.
Sì?
Sorry, can you go back to the plot of the quaternion?
Yes. Okay, so
yeah, because I had the same problem, but I inverted the desired quaternion, not body quaternion. And because if you look at plot, the quaternion components are different. For example, the yellow line of the desired quaternion and body quaternion are not the same.
you're right. Q3 and Q3, they should be both yellow.
Actually, they're all flipped.
Yes, they're flipped. Exactly.
Yeah.
Yes, exactly.
And I had the same problem on the definition of the error quaternion, but I inverted the desired quaternion, not the quaternion which comes out from the integration of the kinematics.
Oh, why is that? I mean,
I think that besides the reordering of the Q-desired components, you have to invert the quaternion, right? Because I think that you just reorder the components.
where? You mean in this function?
No. And I think that the QB has to be QB, and the matrix in which there are the components of the Q desired must contain the components of the inverse of the Q desired.
Okay, but let me think. So QE is the one that goes from, so the DCM associated with QE should go from the ECI to the C reference frame.
No.
Do you agree?
No, it should go from the spacecraft to the desired orientation. So from the spacecraft to LDLH. It's your current orientation.
No,
yeah.
I'm talking about the I'm talking about the desired quaternion, so the one in this matrix.
Yes.
So it goes from
LDLH?
So from LVLH to ECI.
I think that's how we did it, right?
Yes. So maybe, yes, maybe you're right. we need to invert this one.
So let me show you, and you know, I do not remember why I wrote it this way. It must have been on a piece of paper I simplified multiple times, and this is what I got.
So
if
I
I
stop
share
sharing.
my screen, I don't know what happens. I think it just overwrites.
Okay.
So this is what I see actually. And consider that there is a transpose at the end of this matrix. So this is how mine is looking like. And again, it may just boil down to this because I manipulated things, and you know, and this is only the remember that we only use the first three, right, of the error quaternion. So I massage the product matrix quaternion so that at the end I only have a 3-component vector, because I don't care about the last component. So
yes, I think this is the result of what Alessia was saying.
Okay, so I mean, I can, if you want to make a test, copy these. But again, it follows basically the slides that we have seen. It's just that you need to be careful about what each quaternion is representing from where to where.
Yes, that was the problem.
So I put it in the chat. You can copy and paste, so you can share again. In the same function, you can try to copy and paste this, but it does seem from the plots you showed me that it is working, except it is flipping them. If you look at the if you look at the lines that you have, each line, if you change the sign of it, say to the plot to on the right or the left, they will match actually.
Yes, but in fact,
they go on top of each other.
Yes, in fact, in the error quaternion, then the error quaternion where I then inverted the body quaternion has the correct plot is this one. Is essentially 0.
Yeah. Trying to run mine. Why is it not running now? Seriously? Very funny.
And then also, yes, for example, I also plotted the omega, and they overlap. So it seems like it's working.
So you solved it. That's done. You don't need any help. Is that right?
I think yes, it's working, but now I'm not sure about the sign. So
let me show you what I see in my plots, which I showed you the first day. And by the way, I did fix that. Remember that reorganization after the function that converts from DCM to Quaternion that you guys found for me. I did change that. Doesn't seem to change the results really, but don't know. It's running now, so as soon as it's done, I'll show you my plots, which hopefully are still the same because I played with this. Okay, so we are good with this assignment. As soon as I have my plots open, it's at 50%. I don't know why it's going so slow. Is it very slow for you as well?
Yes, we changed tolerance in order to make it faster.
Absolutely.
So maybe in the meantime, I can share again and we can compare the matrices. So I mean, I think it's the same that I have, because if you transpose this,
that are different. Yeah, maybe.
Yeah, but then when you transpose it,
not quite. I mean, I don't know. I thought so, but there are some differences, I think.
I mean, if we only look at this first row, it should be the same as your first column, and it is apart from this sign. No, actually, it's not.
Yeah, there are some differences. Alessa, you said that you have exactly the same?
No, I actually changed a little the code, because now I am using the quaternion multiplication of the aerospace block set.
Aha.
to compute the quaternion. Yes, because because there were some issues here, and I need to invert the quaternion, and so to avoid doing something wrong, I use the quaternion, the aerospace block set.
Okay, let's see if in the end this is what you see, though.
Should I stop sharing? Yes.
Okay. Aside from me not putting legends, which is terrible, I believe the red one is the desired quaternion over one orbit, and the black one is the one that tracks it. And they're probably not as exactly identical at the beginning.
Yeah, I also have the same results, but I think that is for the initial condition.
Yeah, no, they don't. I don't want them to be identical. That's what I was pointing at. That there's actually some work done at the beginning, and then it's easy to stay on top because it's a slow motion.
Yeah.
If you start commanding more difficult maneuvers, things will be different. And this is the angular velocity error with the omega e. The difference between the two starts at some value, then it goes quickly down to 0. We can zoom in. But yeah, there's some error at the beginning. And the fact that it resumes here is basically, I believe I start the orbit. I don't want to be mistaken. Maybe it's a perigee. And I believe that this is happening when the orbit speeds up again, and so the angular velocity goes a little bit higher, and so you need to, I mean, we can run these for longer, and you will see that this will go eventually to 0 again, but it's pretty much enough.
Yes, it's what I did. Just
yeah,
the runtime, I set it to 1.1 times the.
Yeah. So see, yeah, I started at perigee. So basically, what's happening is that it adjusts, brings down the angular velocity. Then the angular velocity is actually getting smaller and smaller. Then it speeds up and it reaches the peak again here. And by peak, we're still talking about very tiny numbers, but I guess the controller has to catch up with that. And then I have the wheel angular rates. I don't know if this is what you see. And again, I don't have legends. That's on me. Sorry, I should. But these are the 3 reaction wheel. I mean, the part that accelerates the wheel. We start at 500, as you remember, and they do go up. The gimbal rates almost not used. So one thing that one could try to do is change the gains that I gave you and make the CMG more important, because it looks like the gimbals are not exploited, and that's why the wheels are speeding up, which is not crazy. They're not speeding up too much, but I'm sure there is a way to reduce the values that we see here and keep them lower, and using the gimbals a little bit more. Because if you use the gimbal rates a little bit more, you have that torque amplification term that is, that gamma dot that multiplies omega of the wheel. So you're creating torque from there rather than just big omega dot, which is accelerating the wheel. And then, so yeah, these plots are not that exciting unless you kind of zoom in. These are the wheels accelerations, very small. And then angular velocity of the spacecraft. It should not actually go to 0, hopefully. Because, well, 2 components, yes, but one, this is the one, is the Z one, has to match the angular velocity of the orbit, right? And so you see that 1 is never going to 0, and it picks up again when you get close to the perigee, and it was, it's symmetric, which makes perfect sense because it's the angular velocity of the orbit. Maximum at perigee goes down to apogee here, and then picks up again. So that makes sense. And so this is the angular velocity of the spacecraft that is trying to reproduce the one of the orbit. And I think that's it in terms of plots. Now, one thing that, since you're so ahead of the game with this, that you could try to implement is some physical limitations. First of all, you can change the maneuver. At this point, you have the code. You can demand more from your. You can change the orbit. You can do whatever you want. So you can make it more demanding. But there is a couple of things that we're not coding now that are important. Actually, I would say three, because we have variable speed control moment gyros. The wheel rates cannot go to any number, so there must be a physical limitation to how quickly you can go. And you know, there is a limit that is called saturation. So say that the wheels are given by the manufacturer and they cannot exceed 5,000 RPM. Well, then that needs to be hard coded so that they don't, some saturation of some sort. But the same is also true for the wheels accelerations, because the accelerations of the wheels are given by an actual electrical motor somewhere, and that cannot create an acceleration that is arbitrary. It will have a limit. And the same for the gimbal rates. They must be limited. This is an RPM as well. So one thing you could do is search for CMG's data online and put your own physical limitations if you want in the code, and see if you can push the system to actually touch those boundaries. But that's something that, you know, in reality you will have to avoid that. And yeah. Any questions on this assignment? It seems like everybody's doing pretty well, right? Okay. The gentleman who sent me the gravity gradient code. Shall we look at that one?
Yes, it was me.
Okay. Yeah.
Okay. Should I share it now or?
Sure. Yeah. You have time.
Okay. Okay. I just opened the file. Okay, can you see my screen?
Yep.
Okay. Okay. As I said to you, I was trying to see what happens if I start from initial conditions at the equilibrium point. So when the body frame is perfectly aligned with the orbital frame. So I will come back to the MATLAB script. Okay. Here there is my inertia matrix. I try to stay in the region of stability in the first okay, to say in English, the first quadrante. Yes, and I hope I'm say good, because yes, J2 is greater than J1, that in turn is greater than J3. So I'm in this condition, and okay, here I've given an initial condition in terms of Euler angles with respect to the orbital frame. So everything is 0, and then I converted into the to the Quaternion by exploiting this built-in function angle to quad, and also the initial angular velocity is 0. So okay, I try to.
Before I forget, one quick comment. One thing we could try is also if we want to be in a condition that is, I don't know, but that's probably cheating. I was thinking whether the initial angular velocity actually has to be the one of the orbit. But that's.
It was the same doubt that I had, but I don't know.
I don't know if that's fair, right? And this is a circular orbit, right?
Yes, it's a circular orbit, and if
can I see the initial conditions?
Yes, you
Again?
see
the for the orbit.
Right. Sorry.
I know that we discussed.
Yes.
Oh. Okay. So X, Y. So, so this is an orbit. Okay. And has a velocity only on the y-axis, huh? Okay. It's an inclined orbit. Okay.
Yeah.
Okay, so what is your initial Quaternion?
Okay, I can plot it. I can display it.
Because now this is geometrically such that I cannot do what we were doing yesterday, you know, with the two rotations. Maybe we can, but it's a little more elaborate to do by hands, at least, to visualize by hands.
Okay, of course, obviously my quaternion is the corresponding to 0 angles, but in my case I have put the scalar value as the first one, because by using the built-in blocks I found out that of course it treats the scalar one as the first component.
Yeah.
And that's then going to my Simulink project. Yes.
What is LB? What is LB? So that's the quaternion that represents what?
Sorry, yes. I'll stay for LVLH, and so it represents the body frame with respect to the orbital frame. So LVLH. It's the attitude of the spacecraft with respect to the orbital frame. And I start with the initial condition of the body frame aligned with this orbital frame. And I wanted just to check if the output was diverging from the equilibrium, because I should expect it not.
But the initial conditions for numerical integration of the quaternion of the spacecraft with respect to the inertial reference is not this one; it's something else.
Yeah. Indeed, went to the block, to the Simulink, and I converted these initial conditions here into the initial conditions needed for the Euler equation. So the orientation of body with respect to inertial, I don't know, I call it n, but I should change. But and then I used as initial condition into the Euler equations. So I prefer just to define in the script, in the initialization scripts, the quantities with respect to LVLH, but probably I can change. I don't know if it is useful.
That's fine, but I want to see how you do the rest then. How do you go from that to the inertial?
Yes. Okay, I will open. Okay, I just exploited the block that is elsewhere in the Simulink project that simply give the desired attitude, but I applied to the initial conditions. So just these, and so this part of the block is I can show it. I can show you. Is here. Sorry. No, it's outside. Yes, is here. Is when we want to try to get the command attitude and angular velocity.
Yeah.
So I took exactly the same block and I just used it for evaluate the initial attitude. Because in that block we okay, so the output here is should be correct, but I don't know if there are some mistakes here. And then there is also the doubt about the initial angular velocity, because from the script I have this input, which is the omega 0 of the body with respect to the LVLH that I put 0. And I said, okay, it's the angular velocity of the body with respect to inertial reference frame. Okay. I just said this, but I don't know if it's correct.
No. So that's so you are actually you are assuming. So if you're saying that the initial angular velocity of the spacecraft with respect to LVLH is 0, that means you're moving like LVLH, and so your angular velocity of the spacecraft with respect to the inertial is the same as LDLH, which is not 0.
Yeah, but okay, probably it's a wrong notation I used, but if you see this input 4 comes from my MATLAB script where the initial velocity is 0, and I just output this as the inertial angle, the angular velocity of the body with respect to inertial. So this one, which will actually enter in the Euler's equation, is exactly 0.
It
So
shouldn't be.
it shouldn't be the body with respect to inertial.
Well, it depends what you want. Do you want the spacecraft to be at 0 angular velocity with respect to the inertial, or do you want the spacecraft to be at 0 angular velocity with respect to LDLH?
I want to stay in the equilibrium point, so it should be 0 angular velocity with respect to LVLH.
Then you have to, so you can do it both ways. This way, you're saying that it's actually, if that's the initial condition you use for the numerical integration of all these equations, then your spacecraft is not moving like LVLH. It actually has an angular velocity with respect to LVLH.
Okay, so
instead,
right.
if you want to do something else, the opposite, then you have to assign the spacecraft the same angular velocity of LVLH.
Okay.
Which is whatever the H vector is pointing, multiplied times that square root of mu over, what is it, A cubed? I don't remember.
Okay, so I can, in this case, for instance, I also have the initial condition of LVLH with respect to inertial. I just use this as a initial conditions, in the sense that, okay, for instance, here, I can put just in this way, because here as output I have the LVLH with respect to the inertial, but is already in n is the inertial components, inertial frame components. So I should convert. Okay.
Right. Yes.
Okay. So matrix multiply.
You also, this is a question that we had a few days ago, whether the numerical integrators 1 over s, when they take external initial conditions, whether they take the first one only at the first time step, or they keep changing the initial condition, because this omega now is going to change in time.
The omega of the body with respect to the inertial.
Yes, and so you are using it as initial condition the first time step, but then is the numerical integrator forgetting? I mean, because it keeps getting this thing as an input, as initial condition input, and I don't know if that's how it's supposed to work. Remember, I couldn't find the answer last time. Basically, yeah, you have a block 1 over s that takes, you can type in the initial condition in the window that opens when you double click, or you can select that the initial condition is external and it comes in from the signal. So if that signal is not coming from just a constant, but it's coming from something that varies during the simulation, I don't know how the integrator block is behaving. That's what I'm asking, I guess. In other words, is it really using just the first time step value of that signal that comes in as initial condition, or is it doing something else? So. You don't know? Because that could be another major problem.
Yeah, I think that it should be take only the first values unless you set some reset options.
Okay. To be honest, given the small values of angular velocity, it shouldn't make a difference whether you start moving like LVLH or not. I don't think, but is it running or you're still modifying things? You're muted. I don't know if you can hear me.
Sorry. So I was
No,
speaking this time. Okay, sorry. No, I'm trying to run it, but I don't know why it doesn't allow me to do it, even though I'm not modifying anything, and anything is running right now. So okay, let's check again. Okay, I can try to to close everything down and reopen.
Oh,
Probably.
It's frozen?
What?
It's frozen?
Yeah, it doesn't allow me to push the run button. I don't know why. So I will try to brutally close everything and then reopen.
Okay.
Okay. But probably I have more than one open. Okay. Okay.
You didn't lose the
modifications. No, because I have saved, I think. But we'll check. Okay. Okay. Let me check first if the modification has not been destroyed. Okay. Okay. Okay, now here I've plotted the quaternions. Okay, I have not plotted the error quaternions, but probably I should because it's better to visualize. The first one is the quaternion of the spacecraft body with respect to the LVLH, and it should be good because it should stay. One is okay, probably it's not seen very well, but the scalar component is 1 and the other should be 0. I have also made an animation. This is my last check. Nice. About this. I'll try to run.
Like, well, this is too perfect now. It's just staying on top of it all the time.
Yes. So, but I don't know if it's
because that's what I thought. That it's cheating in the sense that you put your spacecraft exactly like LVLH. It's moving exactly like LVLH.
Exactly.
And I don't know whether gravity gradient is really doing anything to keep it that way, or it's just that it just continues to move that way.
Yes, that's what I was thinking, because by putting okay, sorry.
No, go ahead.
No, yeah. the bikes makes a lot of make a lot of noise. Sorry, the motorbikes in the streets. No, I was just thinking that, as you said, if I put as initial condition the angular velocity of the LVLH, I'm not enabling the gravity gradient to act as a stabilizing force.
Yeah. Well, let's see what it is now. Let's see what it does.
Okay, I will run.
Good. The animation, right? You were talking
about. Yeah. I was running the animation. But okay. I don't know if you see.
Nice. Oh yeah, so it's super perfect, right?
Yeah. Of course, I've already checked the animation without using the gravity gradient, and it does what I should expect.
Okay, so instead, if you go back to what you had before and you put 0, 0, 0, what does it do?
Yes.
It's very unstable, or?
It's very, very unstable. I can show you.
Okay. That's interesting.
Okay, I will put again. Okay, now I need to modify something. Okay. Actually, my initial conditions are all 0. So also the angular velocity now is 0. I run the Simulink. Okay. I first plot the quaternions. And you see, I see this behavior. And
well, it's trying to stabilize. No, what is it
doing? Yes, but it probably, in order to visualize this in animation, I should run more than one orbit period if it is like this. So I can try. I can go to simulink.
It's going to a specific angle.
Yeah. I will run 3 orbit periods.
That's weird.
And yes, there's a stable, a stable state.
I have, and this is me just, shooting in the dark here, but I'm wondering whether the distribution of moments of inertia is correct, because, see, you have the first moment of inertia, x, the second, and the second is the highest, correct? Yes. So, but we've been playing with x, y, and z now. We're going to point the z down. The way you're setting up the initial conditions, you're going to point the body of the z down because that's A3, correct?
Yes, because the A3 is the minimum one. So
you're going to put the maximum one along the angular momentum?
Exactly.
Okay. And the x is along the A1, which is the roll direction.
Yes.
But it's stabilizing. What are the other angles again?
The Euler angles all the initial one.
No, at the
at
end.
The end.
It stabilizes in which position?
Yes, I have. Okay, the plot of the Euler angles is it's like this.
No, but I mean, it's just jumping. It's the same value.
Yeah, I will try to.
What do you go?
Oh. Let's see. Let me check. Okay, these are the Euler angle.
What sequence is this? Is it a 3, 2, 1?
Yes. The first one is phi, and the last is psi.
Yeah, but the second one is 90, which is the singular case.
Yes.
Not very useful, because you're basically saying that the first and last can be anything as long as the difference is the same. And in fact, I think they're canceling each other. So I'm thinking what's happening here. Okay, it's a 3, 2, 1, right? So x, y, z, either 180, either 90, or another 180. It's flipping in some way.
Yes, but it looks like that the gravity gradient is destabilizing, in the sense that it moves to another completely point of equilibrium.
Stabilizing with respect to another orientation, yes.
Yeah, yes.
And I'm trying to understand what that orientation is. So let's think about this. Assuming that we want to accept this sequence, I'm going to use my overhead camera if you stop sharing for a second, right? So you have the other angles that are psi is 180, theta is 90 and phi is 180, and it's a 3-2-1 sequence.
Yes.
And so if I start from the x, y, and z, and this would be the LVLH basically, the first rotation goes all the way here with the x-axis. So I have an x prime here and a y prime that is here. And then, so y is pointing that way. There I do a 90 degree positive. Is that way, right? So my x goes down here, and my z goes here. And then you do another 180 about this one. And so gosh. Yeah, to me it looks like your spacecraft will point with the final orientation will be with the z of the spacecraft pointing like this, the x of the spacecraft pointing like this, and the y like this. Is that right? Does it make sense?
Okay. Yeah, I can try to run the animation and see what happens at the end.
Yeah.
Yeah. I share again my screen if you want.
Mm-hmm.
Okay. Yes. Okay. So starting from okay, you see that starting from initial conditions aligned to LVLH, it really diverges. And okay, probably is very slow. But after one orbit, we should see the final equilibrium.
Yeah. Yep. Have you tried to increase the second moment of inertia even more?
I tried. I made some trial, but I don't know if I was forcing something. But I can try again and see what happens. I can stop and put a huge value of the inertial momentum.
It must be something small that's some mistake. That is not. Yeah, just start the 0, just for fun. See what happens.
0.
No. Yeah, no,
sec-
make it bigger. Make it 1500.
Ah, okay. Okay.
Yeah,
Okay.
just
Yeah.
for fun.
Okay.
See what happens. So now you're not starting with the same angular velocity.
No, I'm starting with 0 angular velocity with respect to the inertial frame.
Mm-hmm. Yeah, we also need to keep in mind one thing, that the analysis we have done is for small angles.
Yeah.
Yeah, look at that. Interesting. Can I look at the other angles?
Yes.
Oh my goodness. No, I mean, you had the plots there. It's definitely not the best.
Yeah, the plot. Okay, no, I should change a little bit. Okay, but in the meantime, I will run the final order angle. But it's not stable. There's not a final configurations like in the first one. Okay, I will first. Okay, no, let's plot better the other angles.
Well, you know, if you increase that second one, the difference between that one and the other ones, it should become more stable, actually, right?
Sorry, I didn't understood. What difference?
I think if you make the second moment of inertia, unless I'm moving to some other regions of the kx kz plane, but I'm wondering, you should make it more stable, right?
Yeah, because I'm always in the first right-left region of the Cartesian graph. So I'm in the stable configuration. So even increasing J2, I should get a really more stable value, more stable situation.
Has anyone else worked on this gravity gradient? I mean, no.
Yes, but it works only for the ideal initial values.
Like what he did before?
Yes.
Yeah, but then in that case, it's perfect. There's not even any oscillation.
No, you are able to track perfectly the orbital reference frame.
Yeah. Yeah, I'm just wondering whether we can find the error or if there is any, and if there isn't, whether we need, yeah, if we're not staying in the linearization region. The other thing you could try is take the previous case where it was perfectly aligned. You have the angular velocities that are exactly the same with respect to ECI, but take the spacecraft angular velocity and change it a little bit to be, 90% of what it should be.
Okay.
Just to be a little bit away from the initial condition. I'm sorry, this is my way to avoid going inside the code and try to debug things.
Yeah.
We keep changing the initial conditions.
Okay, so
No, so basically what you had before,
yeah,
you just multiply times a 0.9.
yes,
Put back the matrix multiply basically, but then change the angular velocity a tiny bit.
yes, I can put again. I can change all the components of the angular velocity.
Yeah, I think so.
Okay, so let's put 0.9. Okay. Okay. It seems better.
I don't know. The Euler angles? Oh, what is that thing doing? That's a second angle.
Yes, the pitch is completely unstable.
The pitch is unstable. How's it doing that? It doesn't make any sense. Go back to your original moment of inertia, 150 maybe. So, but I don't, again, you may have some error somewhere, but I think it's a matter.
It works.
I'm sorry?
It works by modifying a little bit the initial angular velocity.
Oh, you have a different result?
Yes.
Okay. We can take a look at this one and then you share your screen maybe?
Yeah.
Yes.
Cool. Okay. So you share now.
No, Dario, I think that okay, but I can share now.
Sorry, I didn't understand. It was mine. I stopped sharing to allow you to share.
That is perfectly fine.
Okay.
I think that you now can see my screen.
Yes.
Yeah, these are the first angle, but these are the Euler angles of the body with respect to the inertial frame. So I think that it is it makes perfectly sense that
it has to go around every orbit has to go around one time. Yep.
Yeah. And these are the quaternion and the desired quaternion.
Okay. And the quaternion? Oh, I see. Okay. You don't have the Euler angles with respect to LBLH.
No.
But you have the side.
You can.
So that's the quaternion. To the right is the quaternion of LBLH with respect to inertial, and to the left is the quaternion of the spacecraft with respect to inertial.
To the left is the quaternion of the spacecraft with respect to inertial, but to the right is the quaternion of the LBLH with respect to the inertial.
So yeah, you can see that they are pretty much identical. I would still like to see some oscillation. Can you plot them in the same plot? So they shouldn't be exact. Yes. In fact, they're not identical. They're not identical, right?
No, they are not identical. I think that we can see at the end of plot that there are some differences.
Do you have the quaternion error somewhere?
No, but I don't know if I can plot it easily.
Okay, that's fine. But it seems, I mean, from these plots, it makes sense. It would be nice to see the Euler angles as well.
Yeah,
but
okay.
I mean, the Euler angles of the body with respect to LBLH. Good. So yeah, it could be, aside from having some errors in the code or, not transposing a matrix and all that pain with the rotational matrices, which are not really the thing that I love the most. But it could be, you need to be careful because the analysis is good when you're pretty close to that motion. And probably if you start your spacecraft completely at rest while LH is moving, even though it's moving slowly, that's fast enough to not be linear anymore. It's possible that the analysis doesn't apply. But it's interesting that it's stabilizing in a new configuration, which is, possibly true.
Okay. Yes. Sorry, Alessia, did you try to start from initial conditions like I did? So align.
No, I have the initial values defined in the initialized script here.
Okay.
So for the spacecraft, you have what?
So the ideal orientation, so it means that at the initial time, the body is aligned with the orbital frame, and omega is the 90% of the ideal initial, the orbital angular velocity.
Oh, but see, she is doing the 90% before the matrix multiply. That's also what's happening. Because this is the omega angular velocity expressed
in the LBLH frame.
Right. So, Mr. Pisanti, maybe you can try to do that. Put that point line before the matrix multiplier, because I think that's what's so. Because you first you transform it into inertial, and in that case you have three components. So yeah, that could be a difference.
Yes. Okay, I can
what moments of inertia do you have, Alessia? What do you have? Moments of inertia? The ones that
I think that are the same.
Yeah. That's great. Can you all, for those who have also added gravity gradient, if you can send me that code as well, that would be great. I mean, you don't have to. Yeah. You don't have to, but if you do, I'll recycle it for another class. That's how we survive. What do you think? even though I have to say that using someone else's software is 90% of the times impossible and painful, unless they're very good at simplifying things and commenting. I had a PhD student, the one who worked on the re-entry problem, is very smart, but trying to understand his MATLAB code is it's impossible. Anyways, so do you want to go back and share Dario's screen? Maybe?
Yeah.
Share.
Yes.
Thank you.
I'm not sharing, right?
No.
Okay.
So let's do this. Make the change. The 90. Oh, you did already.
Yeah, I put. I did it, and that's what I get in Quaternion.
Okay.
This is spacecraft with respect to LVLH, and let's see the Euler's angle are this one. So for me, it's not stable in the pitch.
That's weird.
But in Alessia, you found out that it was stable in the pitch.
Well, she doesn't have this plot. Maybe if she can work on this plot, we can make a comparison. She has
okay. Sorry, I didn't understood.
She has the Quaternion plots. I'm wondering if this thing is an artifact of something, because it's jumping between 90 and minus 90. So I wonder if this is true.
Probably yes, because the Quaternion should be quite stable. So I don't know if it explains why I have this jump between 0 and 90 degree. But
how do you extract the Euler angle?
Yes.
The Quaternion, the relative Quaternion.
Okay, let's see. So no, I just put as output from the Simulink. I will check Simulink. Okay, no, it's outside. No, yes, I just used the built-in function.
Yeah.
And I converted in degree, and then.
Yeah. I don't know about those functions. I never use them. Can you double click on that function? I'm not saying that it doesn't work, but it's just that we don't know exactly what it's doing. So you're doing the ZYX.
Yes.
ZYX. Yeah.
And the R1 should be psi.
Yeah.
And okay, even if R1 and R3 are not the correct one, the R2 should be theta for sure, and I have instability in pitch. So.
Well, hold on a second. Let me see this. Just for fun. I'm gonna send you my function that spits out the Quaternion, the Euler angle from Quaternions.
Okay.
It's actually part of your assignment homework 1, but just so put in a MATLAB function that it's exactly that, and substitute that block you have. Yes. That's the only place where you use this conversion, right? Or no, you use it somewhere else as well.
No, but really, it does not. I don't use the other place where I use it just for.
Okay, visualization. Okay, fine.
Visualization, but here I don't know. Probably I used it as initial condition. I should check.
Yeah.
No. Okay. So. Okay. Okay. EQ2 should be theta, right? One. Okay. Let's see.
Yeah.
Probably there's. Okay, I just paste it from the chat, but probably there's. Yes, a comment here.
I'll just remove that. Yeah.
And yes. In my what enters in this function as a scalar component k1. I don't know if your code use the scalar component of the quaternion as the first element.
Yes. So you need to switch at the beginning. Yes.
Okay.
Yes. Sorry.
No, don't worry. So your code actually use the fourth as a scalar component.
Yeah. Yeah. Correct.
This AAQ, okay, should not be. Okay. So. Okay, no. But, okay. Here I've put as the first component of Euler vector psi. I don't know if it is correct. If I check on your code, okay, I'm not able to understand if the first Euler angle is phi or psi, but should be phi, right?
Yeah, I need to go back to the actual DCM. I think it's phi. First one, so the one with the one EAQ1 is phi, and then
Okay.
2 is theta, and 3 is psi. I think. Yeah. So let's try this. Whatever happens, we're gonna take a break, 5 minutes, and then we'll be back.
Okay.
What? It doesn't like it.
Let's see.
Why not? First assignment, disturbances class. Oh, can you go inside? Can you go inside the code?
Yes, there's.
Yeah, you removed. I had an assignment that initializes the EAQ being 000.
Right. Sorry.
For some reason, it wants that.
Okay. Okay. Everything fine. Okay, these are quaternion, and yes, it's the same.
Yeah, we need to think about it, but I need to take a break. Yeah. Let's resume at 25, okay? 25 minutes.
Okay.
See you in a little bit.
See you later.